Welcome to the deep dive. Today we're looking at something pretty interesting. How software engineers map out their finished systems, like in the real world. We got some great material on physical diagrams. That's the plan for today.
Exactly. So we're not talking abstract logic here, but the actual tangible pieces of software and, where they end up living once everything's built and running. Think physical structure.
Okay, got it. So the mission then is to figure out how these physical diagrams show the nuts and bolts of a system after it's deployed. The sources mention two key types: component diagrams and deployment diagrams.
That's right, component and deployment. They give different views of that physical reality.
Let's dive into component diagrams first. What are they showing us exactly?
Okay, component diagrams, they focus on the software components themselves and, really importantly, how they connect and depend on each other. The main goal is breaking a complex system down into parts you can manage, reuse, maybe even swap out later.
Like building with modular blocks, sort of?
Yeah, that's a good way to think about it. Independent modules.
So if I'm looking at one, what are the key things I'd, typically see?
Well, you'll definitely see the components. These are the actual physical bits of implementation.
Yeah.
Could be files, libraries, things like that. They have clear interfaces defining what they do. Visually, often a rectangle with a little component label and maybe an icon.
And interfaces. You mentioned they're important. Why is that?
Oh, absolutely vital. They enable what's called loose coupling. Basically, it means one component can change without messing up the entire system. Interfaces define the contract.
Okay, and there are different kinds of interfaces.
Right. You have provided interfaces, that's the services a component offers to others, and then required interfaces, those are the services a component needs from other components to do its job.
The sources had an order component example, I think. How did that illustrate it?
Yeah, activity one. The order component, it might provide functions like, say, add line item or pay, but maybe to apply a discount, it requires an apply discount service, which has to come from somewhere else, another component.
And you can see that connection on the diagram.
Yep, often shown with what they call ball and socket notation. A little circle, the ball, for a provided interface, and a semicircle, the socket, for a required one. When they snap together, it visually confirms that need is met, or sometimes just simple dependency arrows.
Makes sense. The material also mentioned white box views and ports. Are those just different ways to show the same thing?
They offer different levels of detail, really. A white box view actually lists the interfaces inside the component rectangle. Like in Activity 2, the conversion management component showed it provided feed provider and display converter, but needed a data source. You see right there.
Okay.
And proofs are even more specific, like designated interaction points on the component's boundary, useful for complex components.
And what about delegation and assembly connectors? Sounded a bit like internal wiring.
That's a perfect description. Delegation shows how an interface the component provides is actually handled by a part inside the component. Assembly connects different internal parts within a component. Activity 4 had a more complex example, showing multiple components like blog data source and log4j all connected, showing their provides and requires.
Okay, I think I'm getting the picture. Component diagrams map out the software's internal structure, its building blocks. So let's switch gears then. Deployment diagrams. What's their story?
Right, deployment diagrams. These shift the focus. They show the physical setup, how the software actually gets placed onto hardware. It maps the software artifacts to the hardware nodes and shows how these nodes communicate. It's the where it runs picture.
Software meets hardware. So main elements here, what do we see?
The big things are nodes. Nodes can represent hardware resources, think servers, PCs, devices, often marked with device.
Okay.
Or they can be software execution environments like an operating system, a web server, a database system. Those might be marked execution environment. Think of the runtime environment.
And they're connected.
Yep, by links. These are the communication paths between the nodes, usually solid lines, and you can specify the protocol like TCP/IP or HTTP.
I saw something about nested nodes. Is that like software running inside hardware?
Exactly that. You might have a box representing a physical server, a hardware node, and inside that, another box representing the OS, which is a software node, or maybe an application server running on that OS. Activity 6 had that server hardware containing a G2E server. It shows that containment.
And artifacts. Those are the actual files, right? Like .exe or .jar files.
Correct. Artifacts are the concrete physical outcomes of the development process, the executable files, libraries, configuration files. The deployment diagram shows which node, which piece of hardware or environment each artifact gets deployed onto.
And an artifact can manifest a component. What does that mean?
It just means that a specific physical file, the artifact, is the actual implementation, the physical realization of one of those logical components we talked about earlier. The .jar file is the order component, for instance.
Got it. And finally, communication paths. How do they differ from just the links?
They often represent the same lines, the links, but the focus is on the runtime communication happening over those physical connections or network protocols. Activity 7 showed that, well, a web client communicating via HTTP with a component running on a web server, which itself was on a specific OS on specific hardware, it maps the whole chain.
So putting it all together, these physical diagrams, component and deployment, give us this really vital real-world view. One shows the software's internal structure, the other shows where it all physically lives and runs.
Absolutely. You really need both to get the full picture of a system's tangible architecture. It's super important for actually building, deploying, and maintaining the software, especially as systems get more complex.
That makes a lot of sense. So here's a final thought to leave our listeners with. We see software becoming way more distributed, right? Across cloud platforms, edge devices, all sorts of environments. Thinking about that, how might these physical diagrams, maybe especially deployment diagrams, become even more critical in the future just for managing all that complexity and making sure things stay reliable?
That's a great point to ponder. Definitely something to think about.
Thanks for this deep dive today. Really cleared up how engineers visualize the physical side of software.